Today's lesson, we are going to talk about transformations of functions. And we are talking about any type of function, so we are going to kind of talk more generally. For some function f of x, what are the different types of transformations you can have, and what does that look like? So here's the general equation. So say that g of x is your transformed function, and f of x is the parent function. So all the letters A, B, C, and D correspond to some sort of transformation. So as kind of a general overview, the A value represents a vertical stretch or compression. You may have also learned this as a vertical stretch or shrink, so shrink and compression would be the same. The B value corresponds to a horizontal stretch or compression. And then the C value has to do with shifting left or right. And then the D value has to do with shifting up or down. Now what's not pictured here are any negatives that may show up. So either the negatives could be outside of the function or inside of the function. Both would be some sort of a reflection. So we're going to go into each of these in more detail so you know exactly how it changes with respect to the A value or with respect to the B value and so on. So let's start with the A value. So the A value, which corresponds to vertical stretch or compression, if the A value is greater than 1, then your graph, your transformed function, is going to be the graph of the parent function stretched vertically by a factor of A. So for example, if A is equal to 3, then you know that the graph has been stretched vertically by a factor of 3. Now if A is smaller than 1, so we're not talking about negative values here because we know negatives deal with reflections, but say A was equal to 1/2, then the graph of the transformed function g of x is going to be the graph of f of x compressed vertically by a factor of A. So if A is 1/2, then the graph is going to be compressed or shrunk vertically by a factor of 1/2. Now for each of these, I'm also going to give you a very concrete, if you have this certain point on the graph, on the parent function, then where does that point end up in the transformed function? Okay, so for vertical stretches and compressions, if you have x comma y as a point on your parent function f of x, then x comma a times y will be a point on the transformed function. So in other words, you are going to multiply the y value by a. And that's the same regardless of whether it's stretched vertically or compressed vertically. So you would either multiply by 3 or multiply by 1/2, whichever one it is. Okay, example 1, determine the transformations on the following functions. So g of x equals 2x cubed. Well, first, let's figure out what the parent function is. So in this case, we have a cubic function. The parent cubic function is f of x equals x cubed. So in this case, our a value is equal to 2, which means that since a is greater than 1, this is going to be a vertical stretch by a factor of 2. Okay, in the second one here, we have the square root of x divided by 4. So this is a square root function. So the parent square root function is f of x equals the square root of x. And that means that a is equal to 1/4. Now since 1/4 is smaller than 1, we know we have a vertical compression by a factor of 1/4. Okay, now let's move on to the value of b. We mentioned that this is going to correspond to a horizontal stretch or compression, so let's talk more specifically. Now a horizontal stretch or compression is going to be very similar to the vertical stretch or compression, but actually flipped. So when b is greater than 1, the graph of f of x is actually going to be compressed horizontally by a factor of, and then here you have to be very careful, it's by a factor of 1/b. So for example, if b is equal to 4, that means that the graph is compressed horizontally by a factor of 1 over 4. So it's 1/4 the size horizontally. Now on the other hand, if b is less than 1, again, we're not talking about negative values here. If b is less than 1, then your transformed function will be stretched horizontally by a factor of 1 over b. So let's say, for example, b is equal to 1/2. That means that it is stretched horizontally by a factor of 1 over 1/2, which is equal to 2. It's stretched horizontally by a factor of 2. Again, let's talk about specific points. So if xy is a point on f of x, then x over b, comma y, is going to be a point on your transformed function g of x. So just be aware that this x over b is really the same as multiplying by that factor. So the factor is 1 over b, so if you multiply x by 1 over b, that's the same as x divided by b. Take a look at example 2. Determine the transformations on the following functions. H of x equals x over 2 squared. So notice how in this case we have a quadratic, and inside of the quadratic, before it's being squared, we have over 2. So in this case, let's write down what the parent function is. It's just your y equals x squared. And inside of the function, what are we multiplying by? We're multiplying by 1/2. So b is equal to 1/2. Now what does that correspond to in terms of a transformation? Well, b in this case is less than 1, so it's a horizontal stretch, and then it's by a factor of the reciprocal of this, 1 over 1/2, which is 2. So it's a horizontal stretch of 2. Look at the next one. We have g of x equals 1 over 2x. Now this one's a little bit tricky, but notice how the x is in the denominator. So this is the reciprocal function, f of x equals 1 over x. And so inside the function, so right next to the x, before it's 1 divided by that value, so it's within that function, we have a 2, which means b is equal to 2. Now, since b is greater than 1, this corresponds to a horizontal compression by a factor of the reciprocal of this, which is 1/2. So it is compressed by a factor of 1/2. All right, let's move on to the c value. So c shifts it left or right, and this is kind of the opposite of what you naturally think. So if you have plus c, it will shift to the left by c units. If you have minus c, this will shift to the right by c units. In terms of a specific point from the parent function, if you have some point x comma y, then on the transformed function, that's going to be x plus or minus c comma y. All right, and then d shifts the graph up or down. And here, this will be more natural what you normally think compared to your c value. When it's plus d, it will shift it up by d units. If it's minus d, it will shift it down by d units. All right, and then for a specific point, if you have x comma y on your parent function, then on your transformed function, you would have x comma y plus or minus d. Okay, lastly, we have negatives, which correspond to reflections. And so you can have negatives in one of two places, either on the x, which would be inside the function. That would be a reflection in the y-axis. You could also have a negative on f of x, or in other words, outside of the function. In that case, that would be a reflection in the x-axis. Now, if x comma y is a point on your parent function, then For the first one, in the first case, when you have a reflection in the y-axis, then negative x comma y will be a point on the transformed function. On the other hand, if you have x comma y on your parent function and you have a negative on the outside of the function, then x comma negative y will be a point on your transformed function. Okay, now let's combine all these different transformations. So when you do combine transformations, you do want to make sure that you have it in the form that I have written here. In other words, that b value that's inside, you'll notice is factored out. So just as a note, you may need to factor out b, which will result in the c value changing to c over b. Let's look at example 3. List all transformations on the following functions. So g of x equals negative the absolute value of 2x minus 1 plus 4. Okay, so first thing we see here is that inside of the absolute value function, we have 2x minus 1. The 2 is not factored out. So let's deal with that first. When we factor out the 2, think of it as you're dividing everything inside of that function by 2. So this will be 2 parentheses x minus 1/2. Now we can list out all the transformations. So the negative on the outside of the function represents a reflection in the x-axis. We have a 2 multiplying the x inside the function, so that will be a horizontal compression by a factor of 1/2. We have the minus 1/2, which represents a shift to the right by 1/2. And then we have the plus 4 on the outside, which represents the graph shifting up by 4. Okay, let's look at the next one. H of x equals 4, parentheses negative 3x plus 9, parentheses squared, minus 6. So again, first thing we want to do is we want to factor out that negative 3. So that's the same as dividing everything inside the parentheses by negative 3. So this will be 4 times negative 3 parentheses x minus 3 and then squared minus 6. All right, so let's start with the left. We have a 4 on the outside. That means this is a vertical stretch by a factor of 4. We have a negative that's inside of the function, so that's a reflection in the y-axis. Then we have a 3 on the inside of the function multiplied by the x, so that's going to be a horizontal compression by a factor of 1/3. Then we have minus 3, which means this is going to shift to the right 3. And then we have that minus 6 on the outside, which means this is going to shift down 6. Now let's take a look at an example where you have a point and you want to know where that point ends up on the transformed function. So we have 6, negative 8 is a point on f of x. What is a point on negative f of 3x plus 6 minus 4? Okay, so we want to kind of take this one step at a time, look at all the different transformations, and apply that to this point. Now you'll notice here that inside of the function 3x plus 6, that's not yet factored. So let's do that first. So this becomes negative f of 3 times, parentheses, x plus 2 minus 4. Okay, so we should work from left to right, and I'm going to start with the outside. Now you'll notice that everything that's on the outside is going to affect your y value. So starting with the negative that's on the outside, that's a reflection in the x-axis. So that means your y value is going to become the opposite. So 6, negative 8 will become 6, 8. Okay, so that takes care of that transformation. Now we have that minus 4 at the end. That means that your y value will go down by 4. So 6, 8 will now become 6, 4. All right, now let's work on the inside. So on the inside, we have a 3. That corresponds to a horizontal compression by a factor of 1/3. So instead of your x value being at 6, you multiply that by a third, and now it's at 2. So that's going to be at 2, 4. And then lastly, we have that plus 2 on the inside, which means this is going to shift to the left by 2. So instead of being at 2, 4, now your x value is going to change, so it will now be at 0, 4. So you'll notice that the way I worked was I started by working with just the y value and finding that, and that was everything on the outside of the function, so the negative on the outside of the function, and then the minus 4 on the outside of the function. I worked from left to right. Then I looked at the x coordinate, and I looked at everything inside of the function, which would affect the x coordinate, and I worked from left to right. So I worked with the 3 first, and then I worked with the plus 2. And so that's how you always want to go about working with a specific point and coming up with a new point. So work with either the x or the y coordinate first, and then move from left to right. So y coordinate, left to right, x coordinate, left to right. Another way to think of it is outside of the function, left to right, inside of the function, left to right.